Section: Introduction. In this section, we introduce Vision Language Models, VLMs, particularly CLIP, which utilize paired images and text descriptions to create a shared representation for both. This approach allows us to design image classifiers using text descriptions and to generate images based on user-defined text prompts. The effectiveness of this method hinges on the precise alignment of images and text. Although CLIP aims to achieve this alignment through contrastive pre-training on large datasets, it has limitations, such as lacking the structural properties of purely language-based embeddings. For example, while text embeddings can perform vector arithmetic to express analogies, CLIP does not exhibit this capability. Additionally, previous studies have shown that CLIP's embeddings lack geometric properties, have significant gaps between different modalities, and struggle with complex descriptions involving multiple attributes and objects. Since CLIP is widely used for various tasks, accurately capturing meaningful differences between images can enhance performance in tasks like text-to-image generation and retrieval. We propose to align the differences in CLIP's image encodings with meaningful text descriptions of those differences to improve its reasoning about them. Our experiments reveal that these differences are not well represented in CLIP's embedding space. In contrast, large language models, LLMs, can generate meaningful distinctions between concepts. Therefore, we use LLMs to create a synthetic dataset of text descriptions that highlight differences between pairs of images from a dataset like COCO. We then fine-tune CLIP to align these descriptions with the differences in its image embeddings through a contrastive objective, which we call PC CLIP, Pairwise Comparison CLIP. Building on our pairwise comparison approach, we develop a new inference method called comparative prompting. This method aims to enhance performance by incorporating prior knowledge in the form of text descriptions of class differences. For example, when distinguishing between images of a crab and a lobster, we can describe their differences, such as the crab's rounded body versus the lobster's long body and large claws. We use this comparative prompt to refine and differentiate the class prompts for these similar categories. We demonstrate the advantages of our fine-tuning approach through empirical results. PC CLIP gains the ability to perform difference-based classification, allowing it to rank images based on specific attributes like size and color, achieving significantly higher accuracy compared to CLIP. Additionally, PC CLIP shows improved zero-shot classification performance across various downstream tasks, even when compared to baselines that use the same data or non-comparison-based synthetic data. These enhancements are further amplified when we apply our comparative prompting technique with PC CLIP, while using comparative prompting with standard CLIP features can lead to performance drops. Lastly, we show that PC CLIP exhibits better geometric properties in embedding space, enabling more effective manipulation of embeddings for image generation, where additive operations on text embeddings are better reflected in the generated images. In the related work section, we discuss the evolution of VLMs like CLIP and Align, highlighting the focus on prompting as a method to define classifiers using natural language descriptions. Some methods utilize LLMs to extract additional class information, leading to improved performance and interpretability. Other approaches have explored learning language descriptions in various settings or extracting concepts from pre-trained models in a zero-shot manner. Additionally, some works have aimed to use VLMs for generating captions or differences between images. Our work stands apart as it leverages the reasoning capabilities of LLMs to enhance the geometry of CLIP embeddings rather than constructing a VLM directly from an LLM. Section Summary. In this section, we introduce our approach, PC CLIP, which enhances the alignment of CLIP's image embeddings with semantically meaningful text descriptions of differences between images, improving its reasoning capabilities. We demonstrate that this method significantly boosts performance in difference-based classification and zero-shot tasks, while also ensuring better geometric properties in the embedding space compared to the original CLIP model. Section: Fine-tuning. In this section, we explore how to fine-tune vision language models, VLMs, for specific tasks rather than relying on fixed pre-trained versions. We note that various studies have shown that fine-tuning can enhance model robustness. Previous research indicates that large language models, LLMs, can improve or diversify captions in pre-training data, which can lead to better performance. Additionally, we find that when we have labeled data for downstream tasks, aligning fine-tuning with the original pre-training goals is more effective. Some studies also suggest that using multiple LLM-generated class descriptions can enhance few-shot fine-tuning. We also discuss the embedding space of CLIP, where many researchers have examined its characteristics. Some work aims to improve the geometric properties of this space through pairwise distances, although this doesn't directly address meaningful semantic differences generated by LLMs. Other studies reveal that CLIP's embedding space behaves like a bag of words, lacking the ability to associate specific attributes with instances. Furthermore, some researchers create large synthetic datasets to help VLMs reason about visual concepts rather than just individual objects. Our work relates to this by highlighting the shortcomings of CLIP's embeddings and proposing a new fine-tuning method to tackle these issues. We then shift our focus to how natural language can enhance model performance and interpretability. Various studies have shown that using natural language as explanations for model decisions can improve both LLMs and reinforcement learning models. The most relevant work involves grounding explanations to adjust the network's attention or provide detailed descriptions for specific areas of an image. Other research examines visual textual entailment, where the goal is to determine if an image supports a given text description. In contrast, we aim to enhance CLIP's embeddings by focusing on the relationships between objects. Next, we outline our approach to generate natural language descriptions that highlight differences between images using LLMs, and how we fine-tune CLIP to better understand these differences. We propose a method for general difference-based classification, which involves ranking images based on specific attributes, and comparative prompting to utilize relational information between classes for improved performance. We note that while CLIP models are trained using a contrastive learning objective, they surprisingly struggle with making analogies in their embedding space. To address this, we leverage LLMs, which have shown an understanding of comparative information, to generate text that encourages VLMs to better reason about differences in their embedding space. We utilize image caption datasets to create natural language descriptions of the differences between images based on their captions, avoiding the need for expensive human-labeled data. For a dataset of paired images and captions, we use an LLM to generate descriptions of the differences in meaning between the captions. This provides weak supervision to help incorporate explicit differences into the VLM's learned embeddings. We prompt the LLM with a question about the visual differences between images based on their descriptions, along with examples of desired responses. We also filter out low-quality outputs to create a curated dataset of comparisons. Finally, we present our strategy for integrating these LLM-generated comparisons into our VLMs through fine-tuning with a contrastive objective. Given a pair of image caption sets and a description of the difference between the images, we define our objective to align the differences in image embeddings with the corresponding differences in captions produced by the LLM. This approach aims to enhance the geometric structure of CLIP's embedding space, ensuring it reflects meaningful differences highlighted by the LLM. Section Summary. In this section, we explore various fine-tuning strategies for vision language models, VLMs, to enhance their performance on downstream tasks, particularly by leveraging LLM-generated natural language descriptions of differences between images. We propose a novel approach that incorporates these descriptions into the fine-tuning process, aiming to improve the geometric structure of CLIP's embedding space and facilitate better reasoning about visual differences. Section: Difference-based classification. In this section, we discuss difference-based classification, which leverages PC-CLIP's enhanced ability to identify differences in its embedding space. This allows us to create a more versatile classifier that focuses on differences rather than specific class names. We define this task as the ability to accurately identify an image from a pair based on a certain attribute. For example, if we have an image of an elephant and a dog, we might ask, which animal is larger? Our task includes this question and other general differences, like color. This ranking ability can help us build broader attribute-based classifiers or assist in retrieving images that better represent specific properties for future tasks. We can express the loss for this task using a pair of images and a corresponding text difference, such as the size question mentioned earlier. Essentially, we evaluate whether our model can correctly order and labeled images based on a specific attribute by examining their differences in embedding space. This helps us determine if the differences correspond to meaningful concepts like size and color. We note that some features, like size, can be ambiguous, so we focus on the inherent size of objects. Our experiments show that CLIP struggles with this task initially, performing nearly at random, indicating that the contrastive objective alone does not effectively capture relational information between images. Next, we introduce comparative prompting, which allows us to incorporate relational information between classes into our inference process. By using a prompt-based classifier, we can integrate prior knowledge through text descriptions of class-level differences to refine our class prompts. Since obtaining human-labeled image-level differences is costly, we focus on class-level differences, which we can describe efficiently. Let's say we have two classes, A and B, with their respective embeddings. By using a language description of the difference between Class B and Class A, we can create an updated class prompt. This process involves averaging the embedding of Class A with the difference in text embeddings. If our original embedding for Class A is incorrect, we can correct it if our embeddings for the differences in Class B are accurate. This method takes advantage of the asymmetry in text representations, which may be lacking in CLIP. In our experiments, we aim to answer several questions regarding the effects of our fine-tuning. First, can PC CLIP effectively perform difference-based classification across different data distributions? Second, how does our fine-tuning influence the model's zero-shot classification ability? Lastly, does our fine-tuning enhance the VLM's embedding space and its arithmetic capabilities? We demonstrate that PC CLIP can indeed perform difference-based classification on various downstream datasets with significant differences, while CLIP shows almost random performance. Additionally, our comparative fine-tuning does not hinder standard zero-shot classification. Instead, it improves performance with both simple and descriptive prompts in most image classification tasks. We also compare our results against other baselines, showing that our approach outperforms direct fine-tuning of CLIP on COCO and LLM rewritten captions. This helps us isolate the benefits of incorporating comparative information. Finally, we show that PC CLIP's text encoder is enhanced, better aligning class names with their differences and improving image generation for arithmetic operations in the text embedding space, leading to greater classification performance gains with comparative prompting. Section Summary. In this section, we introduce difference-based classification, which enables our model to identify and reason about differences between image pairs based on attributes like size and color, demonstrating that our approach outperforms CLIP in this task. We also present comparative prompting, allowing us to refine class prompts using relational information, and show through experiments that our fine-tuning enhances performance in both difference-based and zero-shot classification tasks. Section: Generating our synthetic dataset. In this section, we describe how we generate our synthetic dataset for PC CLIP fine-tuning, using the Llama 2-13B Chat-HF model. We find that this model produces clearer descriptions of differences compared to the base models that aren't fine-tuned as chatbots. We create comparative pairs from two datasets, COCO and CUB-200-2011, focusing our main results on COCO and deferring CUB results to the appendix. Since the number of pairs increases significantly with dataset size, we generate pairs from 1,000 randomly selected images. After filtering out low-quality outputs, we end up with about 560,000 comparisons from COCO. For evaluation, we test our method on various image classification tasks, including CIFAR 100, Flowers 102, SUN 397, Eurosat, and CUB 200-2011. In our difference-based classification, we create pairs of images from different classes and describe their differences, like stating which image is larger. For the animals with attributes 2 dataset, we use binary attributes to describe classes and generate strings based on differences in these attributes. In CIFAR 100, we use broad labels to determine relative sizes, while in CUB, we generate differences using image captions. For flowers 102, we differentiate colors between groups of yellow and blue flowers. More details and examples are available in the appendix. In our experiments, we utilize a VIT-L14 architecture with pre-trained weights from OpenClip, specifically from Datacomp 1B. We only update the text encoder parameters during fine-tuning, which allows us to pre-compute image embeddings efficiently. For our baseline fine-tuning on Cocoa, we also update just the text encoder parameters using the same 1000 examples from Cocoa that we used for our PC clip dataset. Additional training details can be found in the appendix, and our code is accessible online. We propose a method to enhance CLIP's embedding space by generating language descriptions of image differences, which helps create a more interpretable joint embedding space reflecting differences like size and color. Our fine-tuning allows for effective difference-based classification while maintaining or improving standard zero-shot performance with our updated VLM. Using various metrics and text-to-image visualizations, we find that the PC clip embedding space captures meaningful differences, benefiting downstream applications that rely on clip embeddings. However, a key limitation of our approach is our dependence on LLMs to generate comparisons from imperfect information, which can lead to inaccuracies and hallucinations. This issue may improve with the development of large multimodal models that better understand both images and language, although these models can also suffer from hallucination, resulting in low-quality synthetic data.